So you've all had experience with magnets growing up. This is a magnet I happened to find in a flea market, and as you know, it attracts things made of metal, and if it's not obviously metal, like this plastic coated staple and paper clip, then you'll know that it is metal when the magnet attracts it. Now, this basic phenomenon of a rigid object attracting another rigid object was shrouded in mystery for a long time, and it shows how complicated things are when I have to say that even by the end of this course, you'll only have the faintest idea of what I just showed you. But the basics of magnetic field can be understood at an atomic level quite easily. So we're going to assume that the magnetic field is given to us. So for example, this magnetic field, as children, you may have placed this a sheet over it and put iron filings. Unfortunately, I don't have any iron filings handy, or I would have shown you. Then it creates patterns, and this pattern looks remarkably similar like that of the field of a dipole. So from that, we can conclude at least the magnets that we find lying around our daily life are actually dipoles. Now, why does the fundamental magnet unit have to be a dipole, and why cannot it be like a positive charge or a negative charge? Why does it have to be a plus and a minus together? Remember, a dipole is a combination of plus q and minus q placed a distance d apart. The magnetic case is something like that, except we don't speak of charges in the magnetic case, we speak of the poles. We talk about the north pole and the south pole. So every magnet, even if it's shaped oddly, has got a discernible north pole and a south pole. And one of the things that you may also have learned as children is if you break this into two parts, it again splits up into two magnets. You can never get it down to just a single pole. If you can somehow manufacture a monopole, a Nobel Prize is waiting for you. If you get a north pole or south pole all by itself, you're guaranteed to win a Nobel Prize, because the physicist Paul Dirac showed something miraculous on theoretical grounds. He showed that the existence of a single monopole in the universe implies that charge is quantized. Namely, that all charges free charges, that is, not bound charges, occurs as multiples of the electron's charge. Now, if you have a nucleus and then you can have quarks and so on, and quarks have fractional charges, but we're talking about free charges. So Dirac showed this miraculous statement, and ever since then, people have been trying to find monopoles. There are some indications that monopoles do have to exist if certain string theories are true, and so the hunt for monopoles is still on. Well, keep a lookout for it. If you find it one day, then a trip to Sweden to receive a Nobel is in order. Well, meanwhile, we're going to just assume that the magnetic field is given to us. It is given by nature. One way of giving the magnetic field is to pick a magnet like this and say, I have a magnetic field around it. Another way is to actually simply live on the Earth. It turns out that if you live on this planet, you will have a magnetic field as demonstrated by the existence of what's known as a compass. So actually, I may have a compass right here in my grab bag. So let me sorry about all the clatter. I had to shake out my grab bag, but there it is. It's a compass, and it points to the true north, which means that the true north is this way. Well, actually, the north pole of the magnet points towards the south pole of the Earth, magnetically south pole, but we don't worry about that now. If you want to find the north, then you align the compass, and then it gives you the exact. A compass was Einstein's first early gifts, and it was one of the reasons why he was thinking so deeply about this. It turns out that magnetic fields are very deep, and Einstein showed that magnetic fields and electric fields are two sides of the same coin. Unfortunately, we won't be able to get to that level of sophistication in this course. We'll study still the magnetic field and the electric field as two separate things. The magnetic field is denoted by the symbol B. So that's the symbol for the magnetic field. And the units for magnetic field are Tesla, after the great inventor Nikola Tesla. It is said that Tesla kept a pigeon for a girlfriend. That shows how eccentric he is, or he was. Now a Tesla is very big. A Gauss used to be a smaller unit that was used before, but we'll just stick to Tesla. If you have a magnetic field and out there, what kind of force does any particle feel? The force felt by a particle in a magnetic field, known as Fb, is given by the formula Q times V cross B. Now this shows us many things immediately. It shows us that the magnetic force occurs in a plane that's perpendicular to both the velocity and the magnetic field. So if I have a velocity vector, if a particle is going in this direction, let's say, and the magnetic field is coming out of the page, now I'm going to indicate this as out of the page vector and indicate something like this as into the page vector, because we're now going to be talking about 3 dimensions quite extensively. So the magnetic field is coming out of the page. Let's try to find out what V cross B is. Well, you take your right hand, keep it first along the direction of V, and then move it or curl it in the direction of B. B is sticking out of the page, so if I try to represent them as 3D things, so that is your V vector, that's your B vector, and if you do V cross B, then the direction is going to be in this direction. Well, that's the direction of V cross B. So it's always useful to write that intermediate step first. The direction of V cross B has to be written first. So this is V cross B. And then Q times V cross B is the magnetic force. So if the charge is positive, then the force is going to be in the same direction as V cross B. If the charge is negative, then the force is going to be in the opposite direction of V cross B. So the hint is to always find V cross B first. Then multiply by Q. So this law is complicated. The force is going to be in a direction that's perpendicular, either this way or this way, depending on the sign of the charge, to the velocity vector and the magnetic field vector. So it defines a third dimension. You get lifted off the page if you have a magnetic field. This is in complete contrast with the simplicity of the electric field. Electric field only had Fe equals Q times E. Wherever the electric field pointed, there the charge went. Well, unless the charge was negative, in which case it went opposite the direction of the electric field. Now, the great physicist Heinrich Antoon Lorentz showed that there is a combination of the electric field and the magnetic field that is valid for all speeds, including the speed of light. And this miraculous combination is this. It's QE plus V cross B. In other words, you just simply add them together. You put Fe and Fb together and you get an object that does not depend on how fast you're going. You can be going at any speed. Such formulas are called relativistically invariant. The minute he wrote this, he got a Nobel Prize. That was back in the days when doing something like this got you a Nobel, early 1900s, I think. And it's quite a miracle that all he had to do was put those two formulas together and bang, he got something that does not care about how fast you're moving. What this means is that if you go to a different frame which is moving with respect to this frame, so suppose I'm whizzing by in an airplane, okay? If I'm going by in a really fast airplane, and I measure the effects of this magnet, who knows, I'll probably see an electric field and a magnetic field. Well, whereas when I'm in the ground, I just see a magnetic field. This transformation law shows that the Lorentz force as viewed in the static frame, the frame in which the magnet is not moving, and the Lorentz force viewed in this fast rocket ship or airplane is going to be exactly the same. That's called relativistically invariant. So these are some of the features of the Lorentz force. Now, for the rest of this video, I thought I'd just talk a little bit more generally about the structure of the field lines. So I've already mentioned that the basic unit is a dipole. So if I have a north-south, then that's going to send out magnetic fields from the North Pole to the South Pole like this. And we'll have a chance in one of the experiments to actually measure the magnetic field of a bar magnet, or rather what's called the dipole moment of a bar magnet. So just like you had the dipole moment here, which is called P equals Q times D. Here also you have a dipole moment. It's called mu B. And the dipole moment mu B points from the South Pole to the North Pole. Just like South can be thought of as negative and North can be thought of as positive. So if you have that convention, then mu points from South to North in the same way as P points from minus to plus. So you have this field structure. Now suppose you have some magnetic field. Okay, let's do a problem or something like a problem. Suppose I have a magnetic field from left to right, and that's uniform. I have a uniform magnetic field. Now I also have a particle which is moving at some velocity, which I'll write here, making some kind of angle. Let's make this a 45-degree angle for simplicity. And we'll decide if it's a proton or an electron later. So I want to find the charge to mass ratio of that particle if it's given to me that it does not leave this sheet of paper. Now you may wonder, how is that possible? I just decided here that if I have V and have B, then V cross B is going to be perpendicular to both V and B. So let's do that here. V cross B is going to be into the page. So I have V cross B vector that's into the page. Now how can it be that if I have a vector that's into the page, it doesn't go into the page? How is it that I make the statement that it is still moving on the page? So here's a problem. An electron or an electrically charged honeybee moves in a uniform magnetic field shown. Find the honeybee's charge to mass ratio. So that's the problem I just made up as I was talking. So let's do this. Because it's, let me say it's negatively charged. If it's negatively charged, if V cross B is into the page, the force, magnetic force, FB, must be out of the page. But the only way for the B to stay in this page and not come out is for there to be gravity acting down. And that's where the mass of the B comes in. So I'm going to set FB equal to Fg. In other words, the gravitational force Fg must exactly be equal to Fb. So if I set Fg equal to Fb in magnitude, then I'm going to get mg equals q times v times b sine 45 degrees, because 45 degrees is the angle. And I have my answer, q by m is equal to g over vb, and sine 45 is 1 over root 2. So that's the answer to this problem.